Another application of the exponential function is Newton's law of cooling. The temperature, capital T, of a heated object at time lowercase t is given by big T equals C plus the difference between T naught and C times e to the kt. C is the constant temperature of the surrounding medium. So imagine taking a pizza out of an oven and putting it on top of the oven to cool down. The medium is the air in the room. We're going to assume that's a constant temperature. If you take a hot cup of coffee and you want to cool it down very quickly, so you stick it in the refrigerator, right? Now the air in the refrigerator, or if you take a hot frying pan and put it in the sink, the medium is the water in the sink. T naught is the initial temperature. It's an initial condition, which is the initial temperature of the object. And K is a constant associated with the object that's cooling. So we can model how something's cooling using Newton's law of cooling. So the example I want to go through is the idea of taking a hot cup of coffee and letting it cool down. So I've written Newton's law of cooling at the top, and here's our problem. A cup of coffee is initially 205 degrees Fahrenheit. It is left to cool in a room that is 72 degrees Fahrenheit. After 10 minutes, the coffee has cooled to 185 degrees Fahrenheit. And then the question, how long will it take the coffee to cool to be 175 degrees Fahrenheit? I actually looked up how hot a cup of coffee should be, and I picked this number because it's in the range given by the National Coffee Brewers Association, which I didn't know was a thing until right now. But I know the coffee's initially 205 degrees Fahrenheit, and that's my value for T naught. I place it in a room that is about 72 degrees Fahrenheit in temperature, and that's my constant value C. And so I can start setting up this function. Capital T is equal to 72 plus the difference between 205 and 72, which is 133, e to the kt. When I look at what I'm asked to figure out, I'm supposed to find little t when big T is 175. Well, that would be very easy if I knew a value for k. So I'm hoping that that's what this information is going to help me figure out. So I know when little t is 10 minutes, big T should be 185 degrees Fahrenheit, and that will let me solve for k. So to start, we need to solve this exponential equation for k. After I know the value of k, I'll have the total model for temperature of this coffee cup, and I'll be able to figure out how long it takes it to cool down to 175 degrees Fahrenheit. So let's solve this and find k. 185 equals 72 plus 133 e to the 10 times k. So I need to take 72 away from both sides. So 185 minus 72 is 113. Now I can divide everything by 133. I'm just trying to isolate the exponential part of the equation. So e to the 10k is equal to 113 over 133. I'm going to rewrite this as a logarithm. It's a natural log because I was dealing with a base of e, and now I can just imagine dividing by 10, which I'm going to write as a 1/10 on the other side in a minute, just to make it a little easier to deal with. Okay, so I have the natural log of 113 over 133. Oh, I typed that in wrong. Well, I really should reshoot this, but I'm just going to go with it. So 113 over 133 inside the logarithm, divide by 10. So I'm going to write that k is approximately minus 0.0163. I wasn't given any instructions on how many decimal places to carry here, and since I'm going to use this value to calculate something else, I'm going to carry a few more decimal places. So what we have now is something to plug into K so that we have the model for temperature. T is equal to 72 plus 133 E raised to this value of K, 0.0163 times T. Now I'm asked, how long will it take the coffee to cool to be 175 degrees Fahrenheit? So I can plug in 175 and solve this time for T. So I have to take 72 away from both sides, and again, just isolating the exponential part. So let's see, that will be 103. And I'll need to divide everything by 133. So very similar to the process we went through to find K, except for this time we're finding our final answer, the time it takes. So let's see. That last equation we had written down would have been E raised to 0.0163T is equal to 103 over 133. Rewrite this as a logarithm to get the exponential by itself. Divide by that value of K. And this time we'll see if I can type everything in correctly the first time. So the natural log of 103 over 133 divided by minus 0.0163. And apparently I didn't type everything in. I have an extra set of parentheses there, so we're just going to delete that out, maybe. All right, so natural log 103 over 133 divided by that value minus 0.0163. Now I think I'm ready. And I find that T is about 15.7. It will take almost 16 minutes for the coffee to cool down to 175 degrees Fahrenheit. So, kind of a two-step problem where we have to first find K by solving an exponential equation, and then we had to find little t following a very similar process. One very cool thing about Newton's law of cooling is it's also Newton's law of warming. If our object was cooler than the room we put it into, then it slowly rises in temperature to meet that, and we can use the exact same formulation of Newton's law of cooling or warming to solve those problems.